Hey everyone, welcome to another simple science video, and in this video we are going to be looking at centers of masses. Okay, let's go. Let's kick it off with this simple object. Well, this object has mass, and in truth, it has weight as a result, and its weight acts in a distributed amount across its body. The weight is distributed across its body. Therefore, there are an infinite amount of minuscule of these little force arrows representing the forces acting on the object. So basically, what I'm trying to say is that the weight of an object, like a rectangular block, acts along its surface. Okay. And the great thing about this object is that we can replace all these minuscule little forces by one big force. And the big force is thought to be acting at the center of mass of the object. Okay? So there's a big force that we can represent all these minuscule little forces that act along the surface of the body, and the place where it acts is known as the center of mass of the object. So therefore, we can define the center of mass of an object is the point on that body where all of its weight appears to act. Now, we are going to be looking at simple diagrams of examples of where the center of mass is easy to calculate, easy to find, such as the uniform rod or uniform density rod. That means across its volume or surface, the density of the object remains the same. So if it's a uniform rod, like we will encounter in most of our questions, then we know that the center of mass will be at the dead center of the object. Whilst the uniform lamina, which is basically a 2D sheet, the center of mass will be at the center of the lamina. Whereas in a uniform cube, the center of mass of the uniform cube is at the center of the cube. It's in the coordinates, well, it's at the center of the cube. And what's great about it is because we know that when we take moments about the center of mass of the object, there will be no resultant moment because we replace the entire minuscule amount of forces by one big force. And if we were to take moments about that force, there would be no moments. So therefore, if you take the pivot at the center of mass of an object, it will have no resultant moment. Okay? Now, if you were to take the pivot off the center of mass, there will be a resultant moment. And that resultant moment is calculated as if there's one force acting on that body. For example, the center of mass of this object acts in the middle of its body, and this object has a weight of 10 newtons, and you're asked to calculate the resultant moment. And that's very simple. All you need to do is take the perpendicular distance from the pivot multiplied by the force, and that gives you 4 Newton meters. Very simple. So you're basically replacing the mass of the object, the weight that's spread out across the surface with one force. It's very important when calculating moments, especially when you're considering beams or ladders or bridges. And the next thing is that if in most situations you will have the object placed on a pivot that ain't at its center of mass, and you have to counterbalance the system with something in order for this thing to be in equilibrium. So in this case, the system is in equilibrium, counterbalanced by the mass m, positioned 0.3 meters away from the pivot. So you're asked, find the mass m. So basically, we take moments about the pivot, and it is in equilibrium, so the clockwise moment is equal to the anti-clockwise moment. So we know that the force in which the block acts on the rod is mg, its weight, multiplied by the distance from the pivot, that's 0.3, and on the right side, on the clockwise direction, you have 10 newtons multiplied by 0.4 meters, and that gives you 0.3 mg is equal to 10 times 0.4. However, you can replace mg, and you can find m as 1.3 kilograms. So that's very basic, but this is when we're looking at a uniform object where the center of mass is right at its center. But what if the object is not uniform? What if the center of mass is not at the center? How would we find out the center of mass of the object if its center of mass isn't obviously at the center? So what we do is we split, for example, in this situation, we split this shape into two shapes, and we find the center of mass of the two individual components. So remember, so let me tell you, in this picture, we're having a circular mass acting on a uniform rod. So it's literally placed on the rod. Okay, so the weight of the circular mass is F2, and the weight of the uniform rod is F1, and we know that the distance from the distance of the center of mass of the uniform rod is basically halfway of the entire length. So it's at the center of the uniform rod, whilst the center of mass of the circular mass is right at the center of the circle because it's a uniform circle, and that acts x2 distance from the left. And we can also therefore replace these two forces with one big force at the position of the center of mass, which we designate as xc. Okay, and in these exercises we are looking to calculate xc. So how do we find the center of mass of this irregular object? What we do is we take moments about a certain pivot, and we basically say that well, if these forces F1 and F2 can be replaced by one force acting at the center of mass, then surely if we take the pivot at any particular point on the object, then it will create the same total amount of moment about that force. So the total moment of the top and the below diagram is the same if the center of mass is xc distance of a total force of F1 plus F2. So we come up with an equation of F1 x1 plus F2 x2 is equal to big F multiplied by the xc, which is the distance from the pivot from the center of mass. Okay? So we then come up with a rather logical approach to dealing with this question. And the first thing we do is to pick a point on the object as a pivot. So what I like to do is usually pick the leftmost point on the object, and then I'd find out the total moment about that point. And we do this by considering the two shapes, remember? The two shapes, one F1 and one F2. And then we divide the total moment by the total force, which is, we divide that total moment by F1 plus F2. And the answer should give us the distance of the center of mass from that pivot that we have taken. So I've taken it from the leftmost pivot, so the distance answer is the distance from that pivot of the center of mass. Okay, now let's look at an example in which we numerically designate these values. So the first thing we want to do is pick a point on the object as the pivot. So let's pick the leftmost point on the object as a pivot. Okay, and we find the total moment of the force. So we take the left end as the pivot. Okay, and we find the total moment about that end, that pivot. So we have 6 multiplied by 1.5 meters, add 5 times 2, and that should give us 19 Newton meters. And then we divide this total moment by the total force, and the total force is equal to 6 plus 5 newtons, 11 newtons. So we take 19 divided by 11 and gives us 1.72 meters. So the center of mass of the object is 1.72 meters from the left end. Okay? So it's the big force, F1 plus F2. It's the big 11 Newton force acting at the center of mass. Thank you for watching my video, and if you find these videos really helpful for you, then please do watch my previous videos, as you don't want to miss out any information. And furthermore, please like and subscribe to my channel. I really much appreciate the support, and thank you very much. Have a nice day.